When we picture comets, we often think of brief apparitions, a bright tail in the night sky, a news headline, a few photographs, and then darkness again. But on the scale of the solar system, a comet is not a firework. It is a tiny, mobile laboratory that has been cold stored for billions of years. Far beyond the orbits of the inner planets, in regions where sunlight is weak and temperatures hover only a few tens of degrees above absolute zero, fragments of the early solar system drift in slow, elongated paths. Many of these are comets, small, irregular nuclei a few kilometers across, made mostly of ice, dust, and carbon-rich material. Out there they are almost perfectly quiet. Their surfaces are so dark they reflect only a few % of the light that hits them, more like charcoal than fresh snow. Nothing about them looks dramatic, until they fall inward. As a comet's orbit brings it closer to the sun, the temperature of its surface begins to climb. Frozen gases such as water ice, carbon dioxide, carbon monoxide, and other volatiles start to sublimate directly into gas. They seep out through fractures and pores, carrying dust grains and organic particles with them. Jets erupt from the shadowed pits and cliffs of the nucleus, feeding a growing atmosphere of gas and dust around the solid core. This temporary atmosphere is the coma. The sun's radiation pressure and the solar wind stretch part of it into a dust tail and an ion tail that can extend millions of kilometers downstream. For planetary scientists, this awakening is an opportunity. Most of the material now streaming away from the nucleus has barely changed since the solar system was young. Locked in ice for 4.5 billion years, it preserves the mixture of elements and molecules that existed in the original protoplanetary disk. Spacecraft like ESA's Rosetta have flown directly through this environment, sampling the gases and dust of Comet 67P Churyumov-Gerasimenko and revealing a chemistry rich in water, carbon-bearing molecules, and complex organics. Other missions and telescopic observations have shown that comets can carry everything from simple molecules such as carbon monoxide and methane to more intricate compounds related to the building blocks of proteins and membranes. In that sense, each active comet is a natural experiment. Sunlight supplies energy, ices and minerals provide raw ingredients, and the coma becomes a three-dimensional reaction chamber. By measuring which molecules are present, in what proportions, and how they change as the comet moves closer to or farther from the sun, we can reconstruct both its internal composition and the chemical history of the region in which it formed. This episode focuses on that chemical story. Rather than tracking orbital mechanics or cataloging famous comets, we will ask four connected questions. First, what did Rosetta actually find in the gases and dust of 67P? And what does that tell us about comet interiors? Second, how do other comets, including rare interstellar visitors like 2I Borisov, expand the picture of what typical comet chemistry can be? Third, could comets really have delivered part of Earth's water and a starter kit of organic molecules to the young planet's surface? And finally, when we place comet chemistry in a broader cosmic context, does life on Earth look like an improbable accident, or a natural outcome of the way chemistry behaves in cold, dusty disks around stars like the sun? In the glow of each passing tail, we are not just seeing ice turn to vapor. We are watching ancient chemistry switch back on, and, perhaps, glimpsing the first steps on the road from simple molecules to living worlds. When ESA's Rosetta arrived at Comet 67P Churyumov-Gerasimenko, it was the first time a spacecraft had not just flown past a comet, but settled into orbit it for years. Instead of a single snapshot, we got a long, continuous record of a small world waking up as it fell toward the sun. Rosetta's instruments watched 67P change from a dark, frozen nucleus to an active, venting body surrounded by a growing cloud of gas and dust. Philae's short-lived landing added a brief, close-up look at the surface itself. Together, they turned 67P from a fuzzy point of light into a chemically rich, three-dimensional laboratory. At the heart of this experiment was the coma, the thin atmosphere that forms when sunlight heats the nucleus. Rosetta's mass spectrometers tasted this gas directly, molecule by molecule. As expected, water vapor was the dominant ingredient, HO flowing off the surface as ice sublimated. But water was only the starting point. Mixed into the coma were major volatile species such as carbon monoxide and carbon dioxide, along with a zoo of additional molecules. Simple organics, molecules built from carbon, hydrogen, oxygen, and sometimes nitrogen, showed up clearly. Alcohols like methanol, small aldehydes such as formaldehyde, sulfur-bearing compounds, and a variety of hydrocarbons were all identified in the plume escaping from the nucleus. As Rosetta followed 67P along its orbit, the relative amounts of these gases changed with time and with location on the comet. Some regions released more carbon monoxide, others more water, and the overall composition evolved as the comet approached and receded from the Sun. This was crucial. Instead of guessing comet chemistry from a single pass, scientists could watch how different ices turned on and off, and how deeply buried volatiles started to contribute as heat penetrated the nucleus. The coma turned into a moving graph of the comet's internal inventory. The solid side of the story came from dust. Rosetta's dust analyzers intercepted and measured tiny grains lifted from the surface, while remote instruments studied how those grains reflected and emitted light. The measurements showed that 67PS dust is not just mineral powder. Silicate grains, broadly similar to the rocky material found in meteorites, are intimately mixed with a large fraction of carbon-rich, refractory organic matter. In mass terms, the organic component is not a trace impurity, it is a major part of the dust. Some grains are essentially composite particles, mineral cores wrapped in complex carbonaceous material that behaves more like a tar than a simple ice. Spectral signatures from this material point to macromolecular organics, large, cross-linked carbon structures produced by long-term irradiation and chemical processing of simpler ices. These are not biological molecules, but they show that nature has no difficulty building chemically complex, carbon-based solids in cold, airless environments. In parallel with Rosetta, analyses of samples from other comets and primitive meteorites have revealed amino acids and related prebiotic species, and Rosetta's detection of diverse organics in 67PS gas and dust fits naturally into that broader picture. Comets are not alive, but they clearly carry many of the raw ingredients that life later reshapes. All of this makes 67P a milestone. For the first time, we could monitor the full chemical breathing cycle of a single comet over years. Which gases turn on first, which organics are released together, how the dust-to-gas ratio changes, how jets and surface regions differ in composition. Instead of treating comets as anonymous dirty snowballs, Rosetta showed us a specific, chemically detailed world whose ices and dust preserve conditions from the dawn of the solar system. The mission transformed comets from distant curiosities into serious candidates in any scenario where the early Earth received part of its water and part of its organic starter kit from beyond the orbit of Jupiter. When you first learn about comets, it's tempting to imagine that once you've seen one, you've seen them all: a small icy nucleus, a bit of water vapor, some carbon dioxide, a dust tail. Rosetta showed us that this standard recipe already hides a lot of complexity. But when we start to look more broadly across many comets, and even into other planetary systems, the picture becomes even richer. Comet chemistry is not one template. It is a spectrum of environments and histories, written in gas and dust. Most comets in our own solar system do share a familiar pattern. As they approach the Sun, water ice begins to sublimate and dominates the gas output near $1, releasing a coma rich in HO mixed with carbon dioxide, CO, carbon monoxide, CO, and a zoo of organic molecules. Spectroscopy from ground-based observatories and space telescopes shows recurring species, simple organics like methane, methanol, and formaldehyde, along with more complex carbon-bearing molecules. In that sense, Rosetta's 67P was not an outlier. It fit into the broader family of typical comets, but with enough internal variety to remind us that typical does not mean identical. Once you start comparing comets carefully, important differences emerge. One of the most striking is the balance between water and highly volatile gases like carbon monoxide. CO is far more volatile than HO. It can remain frozen only in very cold conditions. Comets with unusually high CO or HO ratios likely formed in colder, more distant regions of the protoplanetary disk, or preserved their original ices more gently. Others, with relatively little CO, may have formed in slightly warmer zones or experienced more thermal processing over billions of years. Astronomers have identified comets in our own system whose chemistry pushes toward these extremes. Some are CO-rich, releasing large amounts of carbon monoxide compared to water, hinting that they carry ices that never warmed above very low temperatures since their formation. Others are relatively CO-poor, dominated by water and CO, suggesting formation closer in, or partial loss of the most volatile ices. Even among long-period comets falling in from the distant Oort cloud, the mixing ratios of these gases vary significantly. Each comet effectively encodes the temperature, density, and irradiation conditions of the region where its ices were assembled. The story became even more intriguing with the discovery of interstellar comets, bodies passing through our solar system but born around other stars. The first such object with an unmistakably cometary appearance was 2Ir Borisov. Unlike the elongated, puzzling 1Io Oumuamua, Borisov looked comfortingly familiar, a diffuse coma and tail, brightening as it approached the sun, ejecting gas and dust much like a native comet. But when astronomers split its light into spectra, they found something remarkable. Borisov's coma was extraordinarily rich in carbon monoxide relative to water compared to many solar system comets. That high CO abundance suggests that its ice is condensed in an extremely cold region of its home system, perhaps the outer reaches of a disk beyond the snow lines of many volatiles. In other words, even though Borisov behaved like any other comet when warmed by our sun, its chemistry carries the fingerprint of a much colder nursery. This single object delivers a powerful message. The basic idea of an icy, volatile-rich body is not unique to our solar system. Other planetary systems also produce comets, and at least some of them form under conditions that look very similar to, but not identical with, our own. The fact that Borisov's gas mix is both comet-like and chemically distinct shows that the same physics and chemistry are at work in other disks, but with different local conditions and histories. Taken together, the diversity of compositions we see, among Rosetta's 67P, other well-studied solar system comets, and interstellar visitors like Borisov, turns comet chemistry into a diagnostic tool. Comets with modest CO and familiar ratios of volatiles likely formed in environments analogous to our Kuiper belt or scattered disk. CO-rich comets point to even colder regions, or to storage in places that never experienced significant warming. Variations in organic inventories hint at different radiation environments, different dust-to-ice ratios, and different timescales of formation. Rather than a single recipe, we find a family of related cuisines. Each comet carries its own ingredient list, set by where in the disk it formed, how quickly it accreted, and what happened to it afterward. When we survey many comets, in our system and beyond, we begin to see that every planetary system may host its own menu of icy bodies, some rich in certain volatiles, others depleted, some laden with complex organics, others more austere. These moving chemical laboratories are not just picturesque objects with tails. They are samples of the environments where planets and, potentially, the ingredients for life first came together. When you look at a quiet, dormant comet drifting in the dark, it seems like nothing much is happening. In reality, it is a sealed vessel full of frozen ingredients and latent energy. Deep inside the nucleus, water ice, carbon monoxide, carbon dioxide, methane, ammonia, and other volatiles are mixed with fine dust and complex organic residues in a porous matrix. Temperatures are so low that chemistry slows almost to a halt. Many molecules sit essentially unchanged for billions of years. The structure is not a solid boulder but a fragile, fluffy aggregate with voids, fractures, and tiny channels that will later act as pathways for gas and heat. Everything changes once the comet falls inward toward the sun. As insolation increases, heat begins to seep from the surface into the upper layers of the nucleus. Volatile ices start to sublimate at different depths depending on their volatility. Carbon monoxide and carbon dioxide can begin turning to gas far from the sun, while water ice becomes active closer in. The resulting gases push through pores and fissures, dragging dust and organic grains with them. Jets burst from the surface, carving pits and scalloped cliffs, while an expanding coma forms around the nucleus. At the same time, ultraviolet light from the sun and energetic particles from the solar wind and cosmic rays break molecular bonds in escaping gases and surface ices, driving new chemical reactions on the fly. Laboratory experiments give us a controlled glimpse of what this environment can do. When mixtures of simple ices, water, carbon monoxide, carbon dioxide, methane, ammonia, and others, are cooled to comet-like temperatures and irradiated with UV light or energetic particles, they do not stay simple. Over time, they form dark, tar-like residues rich in carbon, hydrogen, oxygen, and nitrogen, so-called tholins. Within these residues and in the volatile products, chemists find amino acid-like molecules, precursors to sugars and nucleobases, and a variety of small organics that are one or two synthetic steps away from molecules used in biology. Space missions and sample analyses tie these results back to real comets and related bodies. Dust from Comet 81P Wild 2 returned by stardust, and organic-rich material in primitive meteorites from similar reservoirs, contain amino acids and complex macromolecular organics that look very much like the products of those isoradiation experiments. Rosetta's long surveillance of Comet 67P Archerium of Gerasimenko showed that this chemistry is not just a laboratory curiosity. As 67P approached perihelion, instruments repeatedly detected a zoo of volatile molecules venting from the nucleus: water, carbon monoxide, and carbon dioxide, but also methanol, formaldehyde, hydrogen sulfide, simple hydrocarbons, and nitrogen-bearing organics. In the dust, Rosetta's instruments saw silicate grains coated and intermingled with refractory, carbon-rich material. That combination, volatile ices, gas-phase organics, and solid, tar-like residues, matches the picture painted by decades of isoradiation studies. It suggests that comets naturally accumulate and recycle prebiotic molecules over enormous spans of time. Crucially, comets are not just static freezers that keep ancient material cold, they are cyclical reactors. Every orbit brings a new pattern of heating and cooling, sublimation and recondensation, fracture and resurfacing. Volatiles can migrate within the nucleus, freeze out again in cooler regions, and be processed further in subsequent passages. Fresh surfaces are exposed by jets and landslides, while older layers are buried or eroded away. Over millions of years, those repeated thermal and radiative cycles give cometary interiors and surfaces many opportunities to rearrange atoms, build up larger organic networks, and generate families of related molecules. A nucleus that has returned to the outer darkness is not chemically identical to the one that first fell inward. There are, however, clear limits to what we have actually observed. No measurement so far has revealed anything like a self-sustaining metabolism, cellular structure, or genetic system in cometary material. What missions and meteorite studies do show is a rich inventory of prebiotic chemistry, amino acids with both left and right-hand forms, simple carboxylic acids, nitrogen and oxygen-bearing organics, and large, disordered macromolecular networks. These are not life in the sky, but they are plausible feedstock for environments, on young planets or icy moons, where liquid water, energy gradients, and mineral catalysts could take the chemistry further. That is why the question naturally turns toward delivery. During the early, more violent epochs of the solar system, comets and comet-like bodies from the Kuiper belt and Oort cloud would have struck the growing Earth and other terrestrial planets in vast numbers. Each impact liberated a mixture of ices, simple volatiles, and complex organics into the atmosphere, oceans, and crust. Some fraction of the more delicate molecules would have been destroyed by the shock and heat, but modeling and experiments suggest that a significant portion could survive in sheltered niches, inside impact-ejected fragments, in cooler parts of the plume, or in shallow subsurface layers. Over geological timescales, countless such deliveries could have seeded the early Earth with a mixture of carbon, nitrogen, and oxygen-bearing compounds far richer than what might arise from the planet's atmosphere alone. Seen in this light, comets really are moving prebiotic test tubes. They collect simple molecules from the protoplanetary disk, process them slowly in the deep freeze and more rapidly near the sun, and then occasionally spill their chemical contents onto planetary surfaces. Whether life on Earth actually required that external contribution is still an open question. Local chemistry in Earth's own oceans and atmosphere may have been sufficient. But the existence of cometary laboratories throughout planetary systems, ours and, as interstellar visitors like 2I Borisov hint, around other stars, suggests that the raw chemistry of life is not an isolated accident. It may be a recurring outcome wherever ice, dust, and starlight coexist. When we talk about comets and the origin of life, the story always comes back to one simple question. What, exactly, did these icy bodies deliver to a young, still-forming Earth? In the early solar system, our planet was anything but calm. After the main phase of planet building, the inner worlds were bombarded by leftover debris, asteroids, comets, and smaller fragments left wandering after the giants settled into their orbits. Some of Earth's original water may have been retained from the nebula, locked deep in the mantle as minerals crystallized. But the intense heating during accretion, coupled with giant impacts, could have stripped or boiled off large amounts of volatile material at the surface. That's why planetary scientists have long suspected that at least part of Earth's oceans and atmosphere was delivered later, by countless impacts from small bodies carrying their own cargo of ice and gas. To untangle who contributed what, we turn to isotopes, the subtle fingerprints written into atoms themselves. The key ratio for water is deuterium to hydrogen, DOH. Earth's oceans have a very specific DOH value. If you measure the same ratio in comets and asteroids, you can ask, which reservoirs look like they could plausibly have mixed into the ocean we see today? Many Oort cloud comets studied so far have DOH values roughly 2 to 3 times higher than terrestrial seawater, suggesting they cannot be the dominant source of our water. A handful of Jupiter family comets show DOH closer to Earth's, so they may have contributed, but they do not look like the whole answer. By contrast, many carbonaceous chondrite meteorites, fragments of ancient, water-rich asteroids, have DOH ratios very similar to those of Earth's oceans. That points to hydrated asteroids as major suppliers of water, with comets likely playing a more modest, complementary role. But mass fraction is only part of the story. When we shift from how much to what kind, comets become much harder to ignore. Carbonaceous asteroids are certainly rich in organics, but comets add another dimension: volatile chemistry. They carry not only solid carbonaceous material, but also abundant ices and gas phase organics that can be injected directly into a planet's atmosphere and surface environment. In that sense, asteroids may have been the main dish of water and rock, while comets sprinkled in additional flavors, exotic molecules synthesized far from the sun and preserved for billions of years in deep freeze. The delivery process itself is violent but not uniformly destructive. When a comet or asteroid strikes Earth, a significant portion of its volatiles is vaporized or chemically altered in the immense heat of impact. However, model calculations and laboratory experiments show that not everything is lost. Smaller projectiles, oblique impacts, and breakup high in the atmosphere can allow a fraction of organic molecules and even water to survive. Some material can be decelerated in the upper atmosphere as dust and micrometeoroids, drifting down more gently and settling onto the surface or into the oceans. In addition, fragments of impactors can be buried in ejecta blankets or ocean sediments, where they are shielded from immediate destruction and can undergo further chemistry in warm, chemically rich environments. Those post-impact settings may have been as important as the incoming cargo itself. A young Earth likely hosted hydrothermal systems at impact sites, volcanic regions, mid-ocean ridges, and shallow ponds where water, minerals, and imported organics could mix. Temperatures cycling between hot and cool, wet and dry, can drive reactions that link small molecules into longer chains. In such contexts, comet-delivered compounds, amino acid precursors, simple carboxylic acids, nitrogen-bearing organics, would not create life outright, but they could enrich the local inventory of reactive carbon, nitrogen, and hydrogen species. Asteroidal materials, with their own suite of organics, would join the same chemical playground. The result is not a single spark event, but a long, overlapping sequence of chemical experiments conducted by the planet itself. Today, the emerging consensus is that no single source explains Earth's water and prebiotic molecules. Internal geochemistry, particularly at hydrothermal vents, can generate reduced gases and organic intermediates from rock and water alone. Carbonaceous asteroids, as indicated by their isotopic similarity to Earth's oceans and by the organic richness of their meteorites, seem to have delivered a substantial fraction of the planet's water and carbon. Comets, despite likely contributing a smaller share of total mass, demonstrate just how readily complex organic chemistry emerges in cold, irradiated ices, and they almost certainly added their own distinct set of molecules to the mix. Together, these reservoirs show that the building blocks of life are not rare miracles, but natural outcomes of planetary and small body evolution. Seen this way, every bright comet in the sky is not just a spectacle, it is a reminder. Long before there were oceans, continents, or living cells, bodies like these were already weaving organic chemistry into ice and dust. When they struck the young Earth, they were not bringing life itself, but they were helping to stack the deck, seeding a world with the ingredients that, under the right conditions, could eventually learn to copy, to adapt, and to awaken. When you look at a comet through the lens of chemistry, it stops being just a streak of light and turns into something far more universal, a small, icy node in a web of processes that stretches from interstellar clouds to young planetary systems and, eventually, to oceans and biology. The molecules we see in comets are not exotic one-offs. They are part of a repeating pattern in the universe. The same simple ingredients show up again and again, in different environments and different combinations, as if nature were rehearsing the same chemical score on multiple stages. Many of the species identified in Planetary, Comet, and dust are already familiar from elsewhere in astrophysics. Water, carbon monoxide, carbon dioxide, methanol, formaldehyde, hydrogen cyanide, simple organics built from carbon, hydrogen, oxygen, and nitrogen. These do not belong to comets alone. Radio telescopes see them in cold interstellar molecular clouds, where stars and planetary systems are born. Infrared observations reveal them frozen in the dust and ice of protoplanetary disks around young stars. On Earth, meteorites, especially carbonaceous chondrites, carry a similar inventory of volatile-bearing minerals and organic compounds, including amino acids and related prebiotic molecules. From a chemical point of view, comets are one expression of a much larger pattern. Give the universe dust, ice, radiation, and time, and it reliably constructs a library of prebiotic ingredients. This repetition has an important implication. It suggests that the raw material for life is not a rare accident of one star system, but a natural outcome of basic physics and chemistry. Ultraviolet light breaks apart simple molecules like water, carbon monoxide, and ammonia. Energetic particles reassemble the fragments into more complex chains and rings. Low temperatures preserve the products in ices and refractory tar-like residues. Whether in a dark cloud, in the outer layers of a protoplanetary disk, or inside a comet's nucleus, the same broad processes are at work. Comets help us see this clearly because their activity, the release of gas and dust when they warm near a star, puts those products directly in front of our instruments. But there is a crucial gap between chemistry and biology. Having amino acids, simple sugars, or nitrogen-bearing organics does not, by itself, produce a living cell. Life requires long-lived, stable environments where liquid water can persist, steady sources of energy that can drive reactions away from equilibrium, and mechanisms that allow molecules to concentrate, assemble, and eventually participate in cycles of self-replication and evolution. Comets are very good at stockpiling and generating ingredients, but they are transient, harsh environments, low gravity, vacuum, intense radiation during perihelion passages. They are more like delivery trucks than kitchens. The detailed cooking, the steps from raw molecules to membranes, metabolic networks, and genetic systems, is overwhelmingly more complex than any chemistry we currently see inside or around comets. That is why many researchers distinguish carefully between different space life ideas. One extreme is panspermia, the hypothesis that actual living organisms, or at least hardy spores, could be transported between worlds on comets or meteorites and seed life directly. This remains speculative. We do not have evidence of viable life in cometary material, and the combined stresses of radiation, vacuum, and re-entry make survival challenging, even if not strictly impossible for all microbes. A more conservative, and better supported, picture is sometimes called molecular seeding. In this view, comets and asteroids deliver not organisms but building blocks, amino acids, carboxylic acids, nucleobase precursors, and complex organics that can feed into local prebiotic chemistry once they land on a young planet with liquid water and energy sources. This scenario does not require biology to endure interplanetary or interstellar flight. It only assumes that molecules, which we know are robust in space, can be transported and then further processed in more hospitable environments. Seen this way, comets become one part of a larger network of sources that furnish a planet like Earth with its starting inventory. Internal geochemical processes, volcanic gases, hydrothermal systems at the seafloor, lightning in a dense atmosphere, can also synthesize organics from simple gases. Carbonaceous asteroids and their fragments, which fall as meteorites, clearly contributed both volatiles and complex organic material. Comets add another dimension: deliveries of especially volatile-rich, ice-rich material, capable of injecting prebiotic molecules into the atmosphere and surface environments. Earth's early chemistry was likely fed from all of these streams at once. The significance of comets is that they prove how far prebiotic chemistry can go in the deep cold of space, before a planet even exists to receive it. If this kind of chemistry is routine in our own system, it is natural to ask whether it is also common elsewhere. Observations of other stars strongly suggest that it is. In the dense clouds where stars are born, astronomers have catalogued dozens of organic molecules, including simple sugars, alcohols, and nitriles. In protoplanetary disks, ice mantles on dust grains show signatures of water, carbon-bearing species, and nitrogen-bearing molecules similar to those in our comets. Young planetary systems likely form their own belts of icy bodies and comets, which then migrate, collide, and occasionally fall inward toward newly forming rocky planets. If so, then many exoplanets will begin their history under chemical conditions broadly similar to those of early Earth, bathed in organic-rich material, with water and carbon compounds arriving from both local geochemistry and infalling small bodies. That does not mean that life itself is common. The transition from a chemically rich environment to a biosphere is still poorly understood. It depends not only on ingredients, but on architecture, the layout of continents and oceans, the stability of climate, the persistence of liquid water, the absence, or timing, of sterilizing impacts, and a cascade of chance events in molecular evolution. Comets can make that first step, the assembly of a diverse chemical toolkit, easier, but they do not guarantee what happens next. The emerging picture is that the universe is generous with molecules but may be far more selective with long-lived, complex biology. From a philosophical standpoint, this is a subtle but powerful shift. Rather than seeing life on Earth as arising from a chemically barren cosmos that accidentally arranged the right atoms, we see life emerging from a universe that is already busy constructing complex organics in many places. Comets are among the clearest, directly measurable examples of this tendency. They show us that, long before there were oceans or cells, space itself was experimenting with the chemistry that would later make those things possible. Whether that chemistry has led to biology on countless other worlds, or only on a few, remains open. But the starting point, the molecular stage, now looks less like a miracle and more like a recurring theme. For most of human history, comets were omens. Brief visitors, bright and chaotic, painted across the sky and gone. Today, after Rosetta, stardust, telescope spectra, and meteorite analyses, we can say something very different. Comets are not signs from the gods. They are chemical messages from the time before planets had names. Over the course of this episode, we have followed them from the cold outskirts of the solar system to the laboratories on Earth. At Comet 67P Arcturus of Gerasimenko, Rosetta watched a seemingly inert lump of ice and dust awaken as it approached the Sun. The spacecraft measured jets of water vapor, carbon monoxide, and carbon dioxide. It found methanol, formaldehyde, and other simple organics. And in its dust it saw silicates wrapped in complex, carbon-rich material. A significant fraction of that dust was not rock at all, but refractory organics, the kind of tar-like macromolecules that laboratory experiments produce when you irradiate simple ices for long periods of time. Other comets and meteorites have completed this picture. Stardust samples from Comet 81PR Wild 2 and organics locked inside carbonaceous meteorites have revealed amino acid-like molecules, precursors of sugars and nucleobases, and a zoo of complex organic structures. Interstellar visitors like 2I Borisov show that this chemistry is not unique to our own planetary system. From molecular clouds to protoplanetary disks to icy nuclei, we see the same pattern repeated. Wherever there is dust, ice, radiation, and time, simple molecules assemble into more elaborate carbon chemistry. For Earth, comets and asteroids were couriers. Each impact that did not sterilize the surface delivered something. Water locked in minerals and ices, carbon in a variety of molecular forms, nitrogen and oxygen-bearing compounds. Most of the mass that built our planet came from larger, drier bodies, but the chemical accent was likely set in part by these smaller messengers from the outer solar system. They did not bring life itself, as far as we can tell. Instead, they carried recipes, catalogs of what chemistry can do when left to run in the dark for millions of years. The leap from chemistry to biology is still enormous. Life requires stable liquid water, steady sources of free energy, mechanisms to concentrate and organize molecules, and the emergence of systems that can copy themselves with variation. None of that is guaranteed just because amino acids or organics are present. But comet studies have shifted the background assumption. The building blocks of biology no longer look rare or fragile. They look like a natural outcome of ordinary physics and chemistry in icy environments. So when we watch a comet flare in our sky now, we are not just seeing an icy nucleus shedding dust. We are watching ancient materials step briefly out of the deep freeze and into the light, releasing the same kinds of molecules that once fell onto a young, unstable Earth. The water in our cells, the carbon in our DNA, the nitrogen in our atmosphere, all trace their origins back to processes like these, running quietly in regions where sunlight is weak and temperatures are low. On their long, dark orbits, comets quietly carry water, carbon, and starlight-altered dust. When they fall toward a young world, they do more than carve craters. They write chemistry onto its surface and into its atmosphere, leaving behind the first lines of a story that sometimes, on planets with the right conditions and enough time, becomes life. In the next chapter of this series, we will follow that story further, away from free-flying nuclei and down into the hidden oceans. Beneath ice shells and rock, asking where else in our solar system water and chemistry may still be working together in the dark.